Hi, it's time for another math easy solution. Today we'll discuss further into applications of integrals and look further into probability and average values and look at example 2 of the example series and basically go over this example which states suppose the average waiting time for a customer's call to be answered by a company representative is 5 minutes. So this is the average value, and again another way of writing average, the symbol for average or mean is mu, the Greek symbol, which I went over in my earlier video. That's just traditional to use that. So anyway, so the question A states, find the probability that a call is answered during the first minute. And then this one, and then part B says, find the probability that a customer waits more than 5 minutes to be answered. And it's basically, we're given that we need to use the probability density function formula from our previous example for a call waiting time. From example 1, you can see in the video link below, and I just showed that in my last video that the probability density function f of t is equal to, well, 0 if t is less than 0, because you're not going to get a call answered before you even make a call. It doesn't make sense. And then when t is greater than or equal to 0, it's equal to 1 over mu. Again, mu is the average waiting time or the mean value, and then times it by e to the power of negative t divided by mu. So again, this is a negative, and this is a decreasing exponential function. You can learn more about this in my earlier videos and the video links below. So if we're using this, let's look at part A. Well, before we get to part A, let's write this down, because mu is equal to 5. Mu is equal to the mean value or the average. Again, you can write it as average, and its Greek symbol mu. Let's write this a bit neater. This equals to 5. So our f of t, the probability density function, is equal to, let's write this neater, is equal to 0 if t is less than 0, and is equal to 1 over 5 mu t over 5 minutes right here. So this is 5 minutes. So the units of this are obviously 1 over minutes for probability density function if t is greater than or equal to 0. So now let's look at part A. So part A states, find the probability that a call is answered during the first minute. So recall my earlier video, so if you're writing probability that the random variable is greater than or equal to 0, t less than or equal to, this is the variable for our random variable time that we're waiting, and then less than or equal to 1 minute. So we write this probability with a p, the t is between 0 and 1, and then this equals to, like I showed in my earlier videos, is just the area under the curve of the probability density function from 0 to 1. And now this is going to be, this is f of t dt. Now we could just plug in our f of t. So we're only dealing with from greater than or equal to 0 right here, so we just look at this formula and not the 0 one. So this just equals 2 integral from 0 to 1 of 1 over 5 e to the power of t over 5 dt. And now let's look at solving this. And now this is 1 over 5 there. I'll just take it out of the integral. This is a constant. Integral of e to the negative t over 5 is equal to t over 5, and then it's the integral of the exponential function is itself. Now we divide it by the constant, which is negative 1 over 5. Let's do that. Let's write this neater. And then 0 to 1, we evaluate from there, but this is a constant, so we can take it out of this this little bracket right here, but it's 1 over 5, and this is divided by negative 1 over 5. This is 1 over 5, so this can cancel out with this when we take it out, and then this negative, we just take that out as well. So this equals to negative, just to make it simplified to evaluate it, so 0 to 1. So now let's just begin adding these variables inside the 0 1. So this is going to be e to the power of negative 1 over 5, and then we subtract by e to the power of, well, 0. E negative 0 over 5 is just 0. So e to the 0 goes to, well, 1. And then e to the negative 5, that's just e to the negative 5. So this is a negative right here, so this equals to negative e to the negative 1/5 minus 1. Or you could write this as, so I'll just write this out completely. So probability that you have from 0 to 1 is equal to 1. I'll just put the negative inside. So 1, this becomes positive, this becomes negative. 1 minus e to the power of negative 1/5. Yeah, and now when you plug this into the calculator here, put in the Google calculator, so 1 minus e to the power of negative 1/5, we get 0.181. Here, I'll round up to 1.3. So let's go back to here. Let's go back to here. So this equals to roughly, if you're rounding it up, 0.1813, which, well, this equals to, and as a percentage, 18 is times it by 100. So this is just 18.13%. So this is the probability that we get a call answered under a minute. So now let's look at the second part. And the second part is asking, let's go to part B. So part B is saying find the probability that a customer waits more than 5 minutes or more than the average wait time. That needs to be answered. So if it's probably more than 5 minutes, so the probability is going to be, well, t is greater than 5. Let's write this neater. So this is the probability that we wait longer than 5 minutes. So this again is the area under the curve for everything greater than 5 minutes. So this would equal to the integral from 5 all the way to infinity of f of t dt. And since this is an infinite interval right here in this infinite interval in this integral, we can't just solve it directly, so we have to write this as a limit. So this equals to limit as x approaches infinity, and then the integral from 5 up to x. And here we'll write f of t, just plug that in, that's just our 1/5 e to the power of t over 5 dt. So now we just solve this integral like we would normally do, and then we would have to deal with the limit afterwards. So this equals to, again, take this 1/5 out of there, so it's all constant. We can take it out of the integral, and the limit is just a constant, doesn't change anything. Limit as x approaches infinity from 5 to x. Actually, I'll just evaluate this e to the, so like before, this is going to be, write this here, e to the negative integral of exponential functions itself, but I'll have to deal with the exponent, with the constant of the power, so we have to divide by that again, negative 1/5. This is going to be evaluating from 5 to x, and like before, 1/5 divided by 1/5, this cancels out, but we have a negative sign, and again we could take this out of this bracket and out of this limit because it's a constant, it doesn't change anything. So this cancels, and take the negative sign out just to make it easier. So we have a negative limit as x approaches to infinity of, now this is going to be, just write this finally simplified, e to the negative power 5, bracket like this, and then this is from 5 to x like before. So now we just evaluate that, so negative, and always keep the limit out there like that, and now we have e to the negative x over 5 minus e to the, just plug in the 5 now, negative 5/5. Yeah, so now this negative 5/5, that's just, well, e to the negative 1. Or in other words, I'll just write that down here. So now we get negative limit as x approaches infinity, and now we have, let's write this to be easier to deal with the limit by flipping this down. So it's a negative power, so we could write this as 1 over a positive power, x over 5. That's all that it means. That's what the negative power means. And then minus, this is e to the negative 1, which is the same thing as writing 1 over e. So this is a constant. There's no x variable, so this is just 1 over e. And then this one right here, as you can see, when you approach infinity, you get e to the power of infinity, which goes to infinity. So we have a 1 divided by infinity. When you're dividing 1 by a really large number, this just goes to 0. This is approaching 0, so we could just write this as 0. So what we end up having is this limit doesn't affect this. This one goes to 0. This equals to now negative, and then we have this negative 1 over e. So put this all together, we have the probability that we wait longer than 5 minutes is equal to positive 1 over e. And here I'm just plugging the calculator. 1 over e is roughly 0.3678. I'll just round this up to 368. So what we end up having is, let's write that down here. So this roughly equals to, when you round it up, 0.368, which is equal to, as a percentage, 36.8 times by 100. I move the decimal place twice to the right. So yeah, that's 36.8%, or roughly 37%. Yeah, so another note on this, so thus about 37% of customers wait more than the mean waiting time. Again, mean is the average waiting time of 5 minutes before their calls are answered. So even though it's the average, there is less than 50% of people waiting longer. And again, this is because the people who wait really long actually skews the results, and I'll explain that in a later video. Basically, if you were rather interested in the waiting time, that would have 50% of the people waiting more than, and 50% waiting less than. So if you wanted to define the waiting time that just splits the people in half, and how many you expect to wait more, how many you expect to wait less, this particular waiting time would be called the median wait time. So the mean is the average one. Yeah, it's the average one that you're expected to wait, but then the median is the number that splits the people in half. And I'll go over this further in the next video, so stay tuned for that one. Anyways, yeah, so that's all for today. Hopefully you'll learn from this. A pretty interesting example on the mean, and a little bit of foreshadowing for the median, basically showing how that the average value doesn't necessarily split people in half. It just splits, it just finds the average waiting time, which is basically summing up all the total waiting time dividing by the number of people. Anyways, that's all for today. If you'll learn from this pretty interesting video, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.